Cyclic molecules and molecules with rings look like they should add a lot of complexity to IUPAC naming. But over the next 9 examples, let me see if I can prove to you how my naming system makes IUPAC names logical and automatic. Hey there, ninjas. In this video, we're going to look at IUPAC naming of molecules with rings. We'll start fairly simple and work our way up to higher and higher ninja levels. At each step, we'll follow the same process through making the name. And I'll show you the few places where the rules change slightly because we have cyclic rings. This isn't a video about all of the rules of IUPAC nomenclature. I have a different video that lays out all the rules, and I'll link to that video in the description below. In general, every name has 5 parts. Some molecules have stereochemical information. Most molecules have substituents, but every molecule has to have a syllable for the parent, the unsaturation, and the priority functional group. In this video, we won't be looking at molecules with priority functional groups. That's the topic of a later video. Instead, we're going to focus on cyclic molecules and their substituents. Cyclic molecules have a ring component and a straight chain component. The first step of IUPAC naming is to find the longest chain of consecutive carbon atoms. Sometimes that will be the ring, and the ring will be the parent of the molecule. Sometimes the carbon chain will have more carbons and be more complicated, and the carbon chain will be the parent of the molecule, and the ring will be a substituent on that molecule. Both are fine in IUPAC land. The main way to decide which one will be the parent is by which is more complicated or has more carbon atoms. If there are more carbon atoms in the ring, or if the ring is more complicated with substituents, then the ring will be the parent. If the chain is more complicated or has more carbon atoms in the ring, then the chain will be the parent and the ring will be the substituent. Here, the ring has more carbons than the chain, so the ring will be the parent for this molecule. So these 6 carbon atoms in the ring will be the 6 carbons in the parent hydrocarbon. Next, we number the ring to give the highest priority functional group the lowest possible number. This ring does not have any priority functional groups. Alkyl groups, halogens, and ethers are all free substituents that have no priority, so we'll number to give the alkyl substituent the lowest possible number. Because it's a ring, we can put carbon number 1 wherever we want, and we can number whatever direction we want. So because we need to give the methyl group the lowest possible number, by default, it will be carbon number 1. From here, both ways around the ring are the same, so it doesn't matter which direction we number. We'll number clockwise in this example. The next step in IUPAC naming is to give the name of the parent hydrocarbon. There are 6 carbons in our parent hydrocarbon in this molecule. The 6-carbon hydrocarbon is hexane. There's no unsaturation and no priority functional group in this molecule, but hexane will not be the name of the parent hydrocarbon for this molecule. Just the name hexane would imply 6 carbons in a linear chain. Here, because they're in the ring, we need to update our parent hydrocarbon to cyclohexane. The cyclo syllable lets the reader know that these 6 carbons are in a ring as our parent hydrocarbon. We do a lot of work with cyclohexanes when we get to chair structures. So for IUPAC naming, let's be really clear. With the cyclo syllable, the 6 carbons are in a ring. Without the cyclo syllable, the 6 carbons are in a straight chain, and we can't get those two confused. The next step is to list all the substituents and their locations. On carbon number 1, we have the methyl group. This isn't a video on how to name these non-priority substituents, but if you'd like a refresher on that, I have a previous video where I went through the IUPAC naming of substituted hydrocarbons. Now that we've listed all the substituents, we're ready to build the name. We list the substituents in alphabetical order. There's only one substituent, so we'll just start with the methyl. We've gotten in the habit of including the location number with all of our substituents. But for this molecule, the methyl group has to be on carbon number 1 by definition when we defined the numbering system of this molecule. And when groups are numbered by definition and can't be any other way, we can omit the number 1. So we'll start with methyl and finish with our parent hydrocarbon, cyclohexane. The name for this molecule is methyl cyclohexane. We don't need the 1 in front because the 1 is automatic. We don't need R or S in front because carbon number 1 is not a stereocenter. The 2 paths around the ring are identical, and carbon number 1 is not a chiral center. Methyl cyclohexane is the official IUPAC name for this molecule. Let's walk through this next example together. The first task is to find the parent hydrocarbon. There are 5 carbons in the ring and 4 carbons in the substituent. The ring has more carbons and is more complicated, so the ring will be the parent hydrocarbon. The next step is to number the 5 carbons in the parent hydrocarbon to give the highest priority group the lowest overall possible number. In IUPAC rules, halogens and hydrocarbons are non-priority substituents. They're free substituents that do not have priority. So we will number to give the lowest overall possible set of numbers in this case. And that's very interesting, because if we start at the halogen and number around this way, we can get substituents at carbons 1 and 3. But if we start at the alkyl group and number clockwise, we can get substituents at 1 and 3. So how do we know which is going to be the correct numbering system? If the highest priority functional group doesn't resolve it, and if the non-priority functional groups give the same numbering, Our tiebreaker is alphabetical order. So we're actually going to have to come back and number this a little bit later after we've named the substituent. So setting the numbering aside for now, our next step is to name the parent hydrocarbon. There are 5 carbons in our parent hydrocarbon, and the parent for 5 carbons is pentane. Just writing pentane, though, would assume 5 carbons in a straight chain. These 5 carbons are in a ring, so it's not going to be pentane, it's going to be cyclopentane. And there's no unsaturation or high priority functional group that would change the ending of this name. Next, we're ready to list the substituents, even though we haven't quite figured out where they are yet. For halogens, we take the name of the halogen and add O to the end, so somewhere we have a chloro substituent. And the 4-carbon alkyl chain has 1 carbon with 3 methyl groups sprouting off of it. We need to recognize that as the T-butyl substituent. Since we got down to the end of our tiebreakers for numbering the molecule, we number the molecule to give the alphabetically first substituent the lowest possible number. And even here we have to be very careful. To resolve this, we're going to alphabetize by the C in chloro and the B in butyl. We do not alphabetize by the N, S, or T isomeric prefixes on our substituents. B comes before C, so when we number this molecule, we'll give the T-butyl group number 1, and we'll number around to give the chloro group the next lowest possible number, and that will be carbon number 3. So the chloro group will be at carbon number 3, and the T-butyl group will be at carbon number 1. Now we're ready to build the name. The T-butyl group alphabetically comes first, so we'll start with 1 T-butyl, 3 chloro, cyclopentane. Our final step is to glance through the molecule and add any stereochemical labels that are appropriate. There are 2 stereocenters in this molecule. Carbon number 1 and carbon number 3 are both chiral centers. And it works out that carbon number 1 is an R stereocenter and carbon number 3 is an S stereocenter. This isn't a video about how to label stereocenters R or S, but if you'd like more information, I have a 3-step foolproof plan that I invented myself to label stereocenters as either R or S, and I'll put a link to that video in the description below. We put the stereochemical labels out front, so this will be 1R, 3S, 1 T-butyl, 3 chloro, cyclopentane. Pause the video, see if you can come up with the name for this molecule. The first step is finding the parent hydrocarbon. There are more carbons in the ring than any of the substituents, and the ring is more complicated than any of the substituents, so the 7 carbons in the ring will be our parent hydrocarbon. The next step is to number to give the highest priority functional group the lowest possible number. We have no high priority functional group here, so we'll number to give the lowest overall set of numbers. There are several ways we can number this. Each of these could be number 1, and we can number each way either clockwise or counterclockwise, but only one gives the lowest overall set. For example, if we start at this carbon as carbon number 1, the next lowest set would be 1, 3, 4. If we start at this carbon as carbon number 1, its set would be 1, 2, 6. And 1, 2, 6 is a higher overall set than 1, 3, 4. If we start at the carbon over here, the lowest overall set would be 1, 2, 4. And 1, 2, 4 is a lower overall set than 1, 3, 4. So we're going to use this position as carbon number 1 and count number counterclockwise to give the lowest overall set of numbers. The next step is to name the parent hydrocarbon. There are 7 carbons in our longest chain. That's heptane, but it's not going to be heptane because it's not 7 carbons in a row. We'll need to update this to cycloheptane. The next step is to list the substituents and their locations. On carbon number 1, we have a methyl group. On carbon number 2, we have an ethyl group. And on carbon number 4, we have another methyl group. Recall that when we have 2 identical substituents, we bring them together with a numeric modifier and call it dimethyl. Now we're ready to name the molecule. We need to be careful when we alphabetize here. We'll alphabetize by the E in ethyl and the M in dimethyl. We do not alphabetize by the numeric modifier that tells us how many of the group there is. E comes before M, so we start with 2 ethyl, 1, 4 dimethyl, cycloheptane. Finally, we glance through the molecule and account for any stereochemistry in the molecule. This molecule has 3 chiral centers, carbon 1, carbon 2, and carbon 4. Carbon 1 is an R stereocenter, carbon 2 is an S stereocenter, and carbon 4 is an S stereocenter. Bringing them together in the front of the molecule, we have 1 R, 2 S, 3 S, 2 ethyl, 1, 4 dimethyl cycloheptane. Note, we do not combine similar stereochemical labels. We do not combine these to 2, 3, di-S or anything like that. We just list all of the stereocenters in numerical order. Let's work through this next example together. The first step is to find the parent hydrocarbon. While the substituent is fairly complicated, the ring is by far more complicated. The 5 carbons in the ring will be the 5 carbons of our parent hydrocarbon. The next step is to number to give the highest priority functional group the lowest possible number. Again, we have no priority functional group, so we need to number to give the lowest overall set. There are 2 equivalent ways to do this. We could have groups at 1, 2, 3, and 4 counterclockwise, and 1, 2, 3, and 4 clockwise. Without a priority functional group to break the tie, we'll need to use alphabetization to find which carbon will be number 1. So we'll set aside numbering for now and move on to the next step, naming the parent hydrocarbon. There are 5 carbons in the parent hydrocarbon. That is pentane, but it's not going to be pentane, it's going to be cyclopentane. Next, we'll need to list the names of the substituents and their locations. On the far right, at some position, we have a bromo group. Continuing clockwise, next is an ethyl group. The next substituent is a 3-carbon substituent with the forked tongue. That's the isopropyl group. And the last substituent is a complex substituent. We'll need to name that with our complex naming rules. To name groups as complex substituents, we cut the group off from the rest of the parent hydrocarbon, and we name the entire group as a mini-molecule. Carbon number 1 is the carbon that directly sprouts off of the parent hydrocarbon, and then we number it to give the longest overall chain. That means at carbon 1 and also carbon 1, we have a dimethyl substituent. So as a mini-molecule, this group would be 1,1-dimethyl propane. But it's not a mini-molecule, it's a substituent on a parent hydrocarbon. So instead of A and E at the end, we replace it with YL. So this substituent will be 1,1-dimethyl propyl. And we wrap the entire complex substituent in a set of parentheses. Now we're ready to alphabetize, not only for the name, but also to figure out the location numbers of all of these substituents. To alphabetize this list, we'll use the B in bromine versus the E in ethyl versus the I in isopropyl and versus the D in dimethyl. We do alphabetize by the I in iso and the C in cyclo when those are substituents. And for complex substituents, we just alphabetize by the first letter, whatever it is. B is alphabetical before D, so bromo group will be at carbon number 1 and will number around the ring clockwise. That means the bromo is at carbon number 1, the ethyl group's at carbon number 2, the isopropyl group's at carbon number 3, and the complex substituent is at carbon number 4. Putting these in alphabetical order then, we'll start over here with 1-bromo. Next alphabetically is the D in dimethyl, so we continue the name with 4,1,1-dimethyl propyl, followed by 2-ethyl and 3-isopropyl. And then we finish with the parent name cyclopentane. Finally, we glance through the molecule to update any stereochemistry. All 4 of these positions are stereocenters. Carbon 1 is S, carbon 2 is R, carbon 3 is S, and carbon 4 is S. So we put them in numerical order in the front: 1S, 2R, 3S, 4S, 1-bromo, 4, 1,1-dimethyl propyl, 2-ethyl, 3-isopropyl cyclopentane. Notice that when the name got really, really long, the process just got really long. It didn't get harder. It didn't get more complicated. It just got more. Trust the process, trust the logic, and you'll come up with the right name every time. Let's flip the tables a little bit with this next example. To name this molecule, first we find the parent hydrocarbon. This time, the ring has fewer carbons than the longest consecutive chain, and the longest linear chain is more complicated than the ring. So this time, the 5 linear carbons will be the parent, and the ring will be a substituent. Next, we number those 5 linear carbons to give the highest priority functional group the lowest possible number. There is no priority functional group in the molecule. The ring is an alkyl substituent, just like any other alkyl substituent. It's a non-priority functional group. We'll number to give the first non-priority functional group the lowest possible number. For this molecule, then, we'll number left to right for the 5 carbons in the parent hydrocarbon. The next step is to name the parent hydrocarbon. With 5 carbons in the parent hydrocarbon, this is pentane. Here, we would not update the name because pentane means 5 carbons in a linear line, and that is what we have here. It is not cyclopentane. Next, we list the substituents and their locations in the molecule. On carbon number 1, we have the 4 carbons of the ring. 4 carbons would be a butyl substituent, but it's not going to be a butyl substituent. They're in a ring, so we name it a cyclobutyl substituent. Carbon number 2 has the ether substituent. On the other side of the oxygen is a methyl group. That's a 1-carbon substituent. And the way we name ethers as substituent is we use the syllable for the number of carbons. So that would be meth for the 1 carbon. And then we end with oxy to show that it's an ether substituent, not an alkyl substituent. We don't say methyl oxy, just methoxy for the ether substituent. And on carbon 3, we have a methyl substituent. Now we're ready to build the name of this molecule. To alphabetize this molecule, we'll use the C in cyclobutyl. Here they tie up until the O in oxy and the Y in the YL substituent. So alphabetically first will be the cyclobutyl substituent, followed by the methoxy substituent as the next alphabetical, and then the methyl substituent, followed by the name of our hydrocarbon. 1 cyclobutyl, 2 methoxy, 3 methyl pentane. Finally, we glance through the molecule to update any stereochemistry. Carbon number 1 is not a stereocenter. It has 2 identical hydrogens attached. But carbon number 2 and carbon number 3 are both stereocenters. In this molecule, carbon number 2 is an S stereocenter and carbon number 3 is an R stereocenter. That gives us a final name of 2S, 3R, 1 cyclobutyl, 2 methoxy, 3 methyl pentane. Take a minute, see if you can figure out the name for this molecule. The first step is to find the parent hydrocarbon. The ring is the most complicated thing here, so the 6 carbon in the ring will be our parent hydrocarbon. The next step is to number the molecule to give the highest priority group the lowest possible number. We have no priority functional groups in this molecule, so we'll number to give the lowest overall set of numbers. We have another situation where it ties. If we start here, we can get 1, 2, 3, 5. And if we start here, we can also get 1, 2, 3, 5. That's going to be the lowest overall set of numbers. So we need to pause numbering until we can alphabetize the substituent. The next step is to name the parent hydrocarbon. There are 6 carbons in the parent hydrocarbon. That's hexane. But because the parent hydrocarbon is a ring, we need to update that to cyclohexane. Next, we'll list our substituents. At the top, we have an isopropyl group. Next is a chloro group, followed by an S-butyl group, followed by an ethoxy group. In terms of alphabetizing, we do the I in isopropyl, the C in chloro, the B in S-butyl, and the E in ethoxy. So since the B in S-butyl comes before the I in isopropyl, the S-butyl group will get position number 1 and will number counterclockwise around this ring. That puts the isopropyl group at position number 3, the chloro group at position number 2, the S-butyl group at position number 1, and the ethoxy group at position number 5. Now we're ready to build the name. Alphabetically, our first group is the S-butyl group, so we'll start with 1 S-butyl. The next alphabetical group is the chloro group. We'll do 2 chloro, 5 ethoxy, 3 isopropyl, cyclohexane. The last step is to scan the molecule for any stereocenters. There are actually quite a few chiral centers in this molecule, but what I want you to notice is that there is no wedges or dashes drawn anywhere in the molecule. Since we don't have the three-dimensional information for all of these centers, we can't invent it. We can't just make up a wedge or a dash and assign the R or S. So when the wedge and the dash information is not given to you, it is not possible to add the stereochemical labels at the front of the molecule because there's no way to know whether they are R or S. So the final name for this molecule will be 1 S-butyl, 2 chloro, 5 ethoxy, 3 isopropyl cyclohexane. For our last 3 examples, we're going to look at a class of molecules that we call bridged or fused bicycles. These are a lot of fun to name, and they don't follow our traditional rules. Your course might not even require you to name these types of cyclic molecules. But just in case they do, let's go through the rules. To start naming a bicyclic molecule, the first thing we do is we count up all of the carbons in the entire molecule. For this molecule, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 total carbons in this molecule. With 9 C's, the parent is nonane. We're not going to worry about substituents on these molecules. Those get really complicated. We'll just stick with the base bicyclic molecules for now. The next step in naming them is finding the bridge connecting points. And here's what I mean by that. There are 2 carbons in this molecule that are vertex positions from which sprout all of the other rings. For this molecule, it will be the top vertex position here and the bottom vertex position here. It's from these positions that we can get from one bridging carbon to the other bridging carbon without picking up our pencil 3 different ways. The ring around to the left, the ring around to the right, and straight through to the other bridge. Once we've found the 2 bridgehead positions, the next step is to number the number of carbons between the bridgeheads, not including the bridgehead carbon. For the pathway on the left, if we start at the bridgehead carbon, not including the bridgehead carbon, we count 1, 2, 3, 4 carbons before we get back to the other bridgehead. There are 4 carbons in this chain, not including the bridgehead carbon. In the path to the right, not including the bridgehead carbon, we count 1, 2, 3 more carbons before we get back to the bridgehead. The path to the right has 3 carbons in that path, not including the bridgehead carbon. In the path in the middle, there's always a third path. Does not have any carbons in between the 2 bridgeheads, so the number of carbons between those bridgeheads is 0. 0 is a number. That's just fine. Now we have enough information to build our name. The way we build the name for these bridged bicyclic molecules is we start with the word bicyclo, and then in a set of square brackets, we list the number of carbons in each of these paths in descending numeric order with dots in between. 4.3.0. And we end with the name of our parent hydrocarbon, nonane. This molecule's IUPAC name is bicyclo-430-nonane. The hardest part for students is finding these bridgehead carbons and counting the number of carbons in the paths, not including those bridgehead carbons. So a good check your work is that the sum of the numbers in the brackets should be 2 less than the total number of carbons in our parent hydrocarbon. 4 plus 3 plus 0 is 7, which is 2 less than the 9 in the nonane. For our second example, this molecule is drawn in a 3-dimensional perspective orientation, letting you know that this vertical bond is closer to you than this bond in the back. If you're not comfortable seeing it that way, you may wish to redraw it in its flat form. This bottom ring is a 6 ring, and there's 2 carbons in between that ring on our bridge. These are identical molecules. This is the perspective drawing looking at it from the side, and here we have the perspective drawing looking at it from the North Pole. Regardless of how we draw it, the process is the same. First, we count up the total number of carbons in the entire system. Here we have 1, 2, 3, 4, 5, 6, 7, 8. Or if we do this version down here, we have 6 in the ring plus 2 more in the middle gives us 8. With 8 carbons, our parent hydrocarbon is octane. Next, we find the bridgehead carbons, the vertex carbons from which we can get across the ring in 3 different ways. In the perspective drawing, it's where all 3 of the bonds meet, and the same thing in the flat version of the same molecule. Once we've found the bridgehead carbons, we go from one bridgehead to the other, and we count the number of carbons in that path, not including the bridgehead carbons. For the perspective version, the pathway to the left has 2 carbons not counting the bridgehead. That's the same in the flat version. For the path to the right, there's also 2 carbons in that path, not including the bridgehead carbons, and we can find the same 2 carbons in the flat version. And for the middle bridge, there's also 2 carbons in that bridge, not including the bridgehead carbons, and it's the same in the flat version. Whether we view the molecule in the perspective drawing or the flat drawing, we need to get the same numbers no matter what. Now we're ready to build our name. We start with the syllable bicyclo. In square brackets, we list those 3 path lengths in descending order with dots between. Here, they're all the same. And we finish with the name of our parent hydrocarbon. This bridged bicyclic molecule has the IUPAC name bicyclo 2,2,2-octane. I told you these were fun names to build. Pause the video, take a second, see if you can work out the IUPAC name for this last example. The first step is to find the total number of carbons in the entire molecule. The outer ring has 8 carbons in it, and there's 2 carbons in the middle, for a total of 10 carbons. Our 10-carbon hydrocarbon is decane. Next, we find the bridgehead positions where all 3 paths meet, and we count the number of carbons between the bridgehead carbons, not including the bridgehead carbons. In the path to the left, I count 1, 2, 3. In the path to the right, I count 3. And in the path in the middle, I count 2. To put together the name, I start with bicyclo. In square brackets, I list the numbers in descending order, 3, 3, 2. And I finish with the parent hydrocarbon, decane. The name of this molecule is bicyclo 3,3,2-decane. And as our check our work, 3 plus 3 plus 2 makes 8, which is 2 less than the 10 carbons in the entire molecule. This is a good name. If you're starting to feel pretty good about IUPAC nomenclature, great. Keep practicing systematically right up to the exam. The next logical step in your journey is to look at molecules that do have priority functional groups. That's kind of the last natural stop in the IUPAC nomenclature system before we change things up looking at benzene rings. Grab a new piece of paper, hop over to that next video, and I'll see you at the end of IUPAC land.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.